So this is the video on amplitude modulation and its applications and usefulness. There are a couple different topics in this unit, including the introduction, which we will go briefly over what amplitude modulation is. We will go over amplitude modulation in the time domain, AM in the frequency domain. We'll do a phasor analysis on our AM signal, and we will do a power analysis. We will also cover the circuitry in the AM modulator and demodulator. Why amplitude modulation? Amplitude modulation is an important process for making signals more versatile and easier to send. In cases in which we don't modulate our signal, we run into problems with antenna length, in which we have to have unreasonably long antennas in order to receive or send our signal. We can have problems with medium frequency responses, and of course we want to make the best use of the bandwidth we have available. So in this example, you might be able to see we might have some noise here that we are unable to filter out, or some other signals, and we just have a clean bandwidth here and here that we want to use. If we have our message signal here, just in the center, it will be completely drowned out by all the noise. So we want to move our message signal to the clean bandwidths that we have available. So we are going to frequency shift our message using the sifting property, and that's how we're going to modulate, pretty much. Our modulation property is going to be based on multiplying the cosine. So as you can see here, this is the Fourier transform of a modulated signal. In this case, x of t would be our modulated signal, and our cos would be the signal that we are modulating with, or the carrier signal. Okay, so first we're going to do an in-depth analysis of amplitude modulation in the time domain. First, we're going to set up our basic equations. M of t is going to be our message signal, where it is, of course, a sinusoid, and the AM is going to be the amplitude of our signal, and the cosine is going to be the frequency. By simply inserting our message signal into the amplitude coefficient of our carrier signal, and assuming zero phase constant here, we have inserted it, we can get our modulated signal here once we distribute our M of t. This makes our signal much easier to transmit and is basically what we will be focusing on. So here we're going to have a basic graphical view of our signal. It's going to consist of AC, which is the amplitude of our carrier, added to the message signal, all multiplied by our carrier here. So we have M of t here, our message signal. We are going to add AC to that to move it up. And then we're going to multiply that by our cosine in order to get our modulated carrier here, with an envelope in the green here, which traces our M of t. However, we do run into a problem with this that you may have seen on the last slide. If our minimum amplitude of our message signal added to the amplitude is less than 0, or if AC plus MT is less than 0 here, we will distort our envelope. So our actual signal that we want to extract is going to be here. However, our signal that we will extract is going to be distorted to what the green line is right now. So let me just grab the laser pointer. Right here it's going to go up, and here it's going to become distorted. So this leads to some restrictions that we have on at least this type of AM modulation. So we're going to want AC plus M min to be greater than 0, so that our signal, as you can see here, is above the axis, and that will prevent any distortion of the envelope. In addition, we're going to define a new term, our modulation index mu, which is going to be equal to the absolute value of our minimum message amplitude divided by the amplitude of our carrier. And in this case, we are going to want to have our modulation index be between 0 and 1 in order to have no distortion. Next, we're going to cover AM in the frequency domain. So as you can see here, we have our AM signal. This is just a different form than you saw in the last slides, I believe. And once we do the Fourier transform, we are going to have this. So this is going to be our frequency spectrum equation, and this is going to be the frequency spectrum graph. This is the spectrum of the message signal. Basically what will happen is each one of these terms here will become one of these sections on this graph. So we're going to have our original equation here of our AM signal. We're going to multiply this in, and then we are going to multiply this in, and then using some basic trig identities, we are going to split this up into each one of these individual terms. Oh, that's kind of weird. And then afterwards, each one of these terms, we're going to find the Fourier transform. So this is a Fourier transform of the carrier. This is a Fourier transform of the upper and the lower sidebands. Once we copy this over here, we will see our frequency domain response here. So this will be our upper sideband, our lower sideband, and our carrier here. Next, we're going to do a brief phasor analysis on our AM spectrum. Don't worry too much about the math. The math is a bit complicated. Try and focus on the premise of the phasors and how it works. So we're going to take a look at our AM signal again from our last slides. We are going to use those trig identities to split it up into the different terms. Each one of these is again going to be associated with either the carrier, the upper sideband, or the lower sideband. We are going to define these as the real component of x of our carrier multiplied by our complex exponential here. So in this example, our x carrier, which is the amplitude of our carrier, will be rotating at a speed of fc here. Our upper and lower sidebands will be our vectors, x, and they will be rotating at positive fm. In this case, positive is in the counterclockwise direction, and negative fm, which is in the negative direction. And fm is, of course, the frequency of our message signal. However, we do run into some problems when we're trying to actually analyze this. Mathematically, this is correct. However, it's very difficult to visualize and do math when our vectors are moving at different speeds. So we're going to convert them. In this page, we simply convert our vectors so that they are of a different length, but they will move at a constant speed, fc. And once we convert them here, our two will move at the same speed. Once we plot them, we can see our phasor diagram here, with the blue corresponding to the carrier, the green corresponding to the upper, and the orange corresponding to our lower sideband. Our carrier will be rotating counterclockwise. Our upper sideband will also be rotating counterclockwise, while our lower sideband will be rotating clockwise or in the negative direction. When these are all rotating at their associated speeds, the end of our vector will point to our corresponding point on our modulated signal here. If we want to check our work, we can convert our phasor spectrum back into our real spectrum, and of course we will get our original modulated signal back. Next, we're going to do a quick power analysis on the AM modulated signal. So just for review, our normalized power is going to be proportional to the signal squared. So in order to calculate that, we're going to take the integral of our squared signal, and this is just going to be the area of one period divided by the length of that period. So once we apply this to our AM signal here, we have our equation. We're going to sub in our values. Once we distribute all our terms, we're going to get two terms here and here. It's going to average out to 0. So we're only going to be left with this one term here. Again, we're going to do some more algebra and then get it into our final form here. In the green here, our 1 over 2 AC squared and our PC is going to be the power of our carrier, and the 1 over 2 of the normalized power of our message is going to be, of course, our message power. Just remember here that our power in the green here, so the power of our carrier, is actually completely wasted. That signal does not actually contain any useful information that we want. Remember, all we want to do is transfer our message information from one point to another. We don't actually care about the carrier. That possesses no information that we need. So with that information, we can actually do an efficiency analysis on our AM signal. So our efficiency N is going to be the power in the sidebands divided by the total power, which is going to be PM divided by PC plus PM. And if we work out the math, it actually turns out that the maximum efficiency of our AM signal, at best, theoretically, is going to be 50%. This is because the AM signal transmits so much power through the carrier, which doesn't actually serve to transmit any information that we want. Theoretically, the efficiency can be 50%, but in reality, it is often much lower. So that wraps up our overview of AM modulation in the time, frequency, and phasor analysis, as well as an analysis of the power. Next, we're going to be doing an overview of the circuitry involved in modulation. So that's going to be the circuits involved in modulating a signal and, of course, demodulating that signal.